Good morning, students. So last class we discussed about the classification of transmission lines based on length, based on voltage, maybe short transmission line, medium transmission line, long transmission line. Short transmission line is nothing but less than 80 kilometers and voltage less than 20 kV. So in short transmission line, the effect of capacitance is neglected. That's why only resistance and reactance must be considered in short transmission line. Whereas in medium transmission line, the length is greater than the 80 kilometers, that is 80 to 160 kilometers, and voltage is also greater than the 66 kV or 132 kV. That's why here effect of capacitance is considered. Therefore, we have to calculate RLC. For that calculation, the distributed capacitance line is divided and lumped from the condensers, and that capacitance is shunted across the load circuit. So long transmission line is nothing but, and the length of the overhead transmission line is more than the 150 kilometers, that is more than 150 or 160 kilometers, and the line voltage is also greater than 100 kV. So that lines are considered as a long transmission lines. For treatment of such lines, the line constants are considered as uniformly distributed, right? And also we have to discuss in transmission system what are the parameters we have to calculate. The performance of transmission line is studied with the help of voltage regulation and transmission efficiency. What is the voltage regulation? Voltage regulation is always as low as possible, but transmission efficiency is as more as possible. Definition of voltage regulation is nothing but difference between the receiving end voltage and sending end voltage, and it is expressed as receiving end voltage. So then transmission efficiency is nothing but ratio of receiving end power to sending end power. VR IR cos pi R divided by VS IS cos pi S. So after then we go for the performance of single phase short transmission line. How to calculate the voltage regulation, how to calculate the sending end power factor, how to calculate the line losses, how to calculate the transmission efficiency. All are explained with the help of phasor diagram, right? I'm explaining phasor diagram. So this is the phasor diagram for short transmission lines, and then we have to calculate the voltage regulation, sending end power factor, power delivered, line losses, power sent out, and also transmission efficiency. Efficiency is nothing but power delivered to power sent out. VR IR cos pi R by VR IR cos pi R plus I square R losses into 100. So look at the equations. These are all discussed last class. And suppose generally we have to calculate phase values only, single phase values only. After then we have to calculate three phase. Suppose if it is a three phase circuit, first calculate phase values, and then that phase values must be converted into three phase values also. So look at the figure. This is also we have to calculate. Now medium transmission lines. In short transmission lines, there is no effect of capacitance. Capacitance is neglected. But coming to the medium transmission lines, it is having sufficient length and is usually operated at low voltage greater than the 20 kV. So that's why the effect of capacitance is considered. Lines, the line capacitance must be taken into consideration. length of the simple. The line capacity methods to calculate the transmission line. End condenser method, nominal T method, nominal pi method. By using end condenser, in end condenser method, in this method, the capacitance of the line is lumped or concentrated. So this is the end condenser method. So look at the figure. So capacitance is connected across the load. The sending end current is distributed as capacitance current and receiving current. IS is equal to IC plus IR. So look at the figure. This method of localizing the line capacitance at the load end overestimate the effect of capacitance. The figure will show the only single phase of three-phase transmission line, and it is more convenient to work in phase instead of line-to-line values. First, we have to calculate the phase values. After then, we have to calculate the line-to-line values. Let IR is the load current, R is the resistance per phase, XL is the inductive reactance per phase, C is the capacitance per phase, cos pi R is the receiving end power factor, Vs is the sending end power factor for phase only. So there is no phasor diagram. I am explaining the phasor diagram. Already explained the phasor diagram for short transmission line, right? Whatever it may be, first we have to take VR, receiving end voltage is the reference, and current is lagging, right? IR is lagging. VR is taken as reference and IR is lagging. Now here three drops are there: ISR, IXL. ISR drop is always in phase with current IR, and ISXL is always lag 90 degrees. So combination of VR plus ISR plus ISXL is nothing but sending end voltage. But current IS is a combination of IS is equal to IR plus IC. IR is nothing but IR cos pi R minus J sin pi R plus IC means charging current, that is 2 pi FC VR. Now voltage drop per phase ISZ, that is IS into R plus JXL. Therefore sending end voltage is nothing but receiving end voltage plus drop. So sending end voltage Vs is equal to VR plus ISZ, that is VR plus IS into R plus JXL. We know the receiving end voltage, we know the sending end voltage. Therefore calculate the voltage regulation. Vs minus VR by VR into 100. And efficiency, power delivered per phase divided by power delivered per phase plus losses per phase. VR IR cos pi R by VR IR cos pi R plus IS square R. Loss is nothing but total current is sending end current, that is IS square R into 100. So by using end condenser method, some limitations although there is a considerable error, that is 10. And also by using this method we can overestimate the effect of line capacitance, right? This is the end condenser method. Now go for the nominal T method. This is most important. Nominal T method, the whole line capacitance is assumed to be concentrated at the middle point. T means total capacity. So whereas in end condenser, capacity is connected at the end, load end. But coming to the nominal T method, the capacity is connected middle of the line. So look at the figure. C, and this line is off and this line is off. Generally, In end condenser method, C is here, R, XL. But now C is put in middle of the line, therefore the line length will be divided into half, that is R by 2, XL by 2, R by 2, XL by 2. Therefore, this arrangement is full charging current flows over half of the line. The figure, one phase of three-phase transmission line, and it is advantageous to work in phase instead of line-to-line voltages. Let us consider IR. Look at the IR is the receiving end load current or receiving end current per phase. R, resistance per phase. XL, inductive reactance per phase. C, capacitance per phase. Cos pi R, receiving end power factor. Vs, sending end voltage per phase. V1, voltage across the, V1 is nothing but voltage across the capacitor C. Now I am not putting in the phasor diagram as usual. Phasor diagram as shown in the figure. Taking as usual, same receiving end voltage is reference. Taking receiving end voltage VR is the reference voltage. Therefore, receiving end voltage VR is equal to VR plus J0. And load current IR is equal to IR cos pi R minus J sin pi R. First VR is taken as reference, then IR R by 2 drop is in phase with IR, then IR X by 2 is 90 degrees leading. Therefore, combination of VR plus IR R by 2, IR X by XL by 2 is nothing but this voltage across capacitor. Voltage across capacitor V1 is nothing but VR plus IR R by 2, IR XL by 2. Now we don't want this one, we want sending end. Sending end means we have to add extra drops also. So by adding V1 ISR by 2 in phase with IR and IS XL by 2 is 90 degree leading. Now combination of V1 plus ISR by 2 IS XL by 2 is nothing but sending end voltage Vs. Right? For calculation, voltage across C is nothing but V1. V1 bar is equal to VR plus IR Z by 2. That is VR plus IR Z by 2 is nothing but IR means IR cos pi R minus J sin pi R. Z by 2 means R by 2 plus JXL by 2. Capacitive current IC is nothing but J omega VC V1C. Omega means 2 pi F. Sending end current IS is nothing but IR plus IC. Sending end voltage Vs is equal to V1 plus IS Z by 2, V1 plus IS into R by 2 plus JXL by 2. This is the nominal T method. Now go for the another method, that is nominal pi method. సో ఇందాక వచ్చేసి కెపాసిటర్ని మిడిల్లో పెట్టాము ఎందుకంటే టీ కాబట్టి. ఎప్పుడైతే మిడిల్లో పెట్టామో సర్క్యూట్ అనేది రెండు భాగాలు అయిపోయింది, అందుకే ఆర్ బై 2 XL by 2 చేసుకుంది. బట్ ఇక్కడ నామినల్ పై capacitor must be divided into two halves, and one half is connected to the sending end, another half is connected to the load end. But transmission line constants R and XL not divided. So nominal pi method, capacitance of each conductor, that is line to neutral, is divided into two halves. Here capacitance is divided into two halves. One half is being lumped at the sending end, other half is lumped at the receiving end as shown in the figure. It is obviously that capacitance at the sending end has no effect on the line drop. Sending end capacitance there is no problem, but only the problem is capacitance at receiving end. Let us consider IR is the load current per phase, R is the resistance per phase, XL inductive reactance per phase, C capacitance per phase, cos pi R receiving end power factor, Vs sending end voltage per phase. As usual VR is taken as reference. For drawing the phasor diagram, VR is equal to VR plus J0, and IR is not, load current IR is nothing but IR cos pi R minus J sin pi R. First you have to calculate the charging current at load end. Charging current load end is nothing but load side IC1. IC1 is equal to J omega C by 2 VR, that is J pi FC VR. So as usual, you have to take the receiving end voltage as the reference for that receiving end voltage, and IR is the lagging with by an angle pi R. Now ILR is in phase with pi IR, and ILXL is 90 degrees. Now the adding of VR plus ILR plus ILXL is nothing but sending end voltage. Here line current is IL is nothing but IR plus IC1. IL is nothing but, look at the figure, IL is equal to IR plus IC1. Sending end voltage Vs is nothing but VR plus ILZ, that is VR plus IL into R plus JXL. Charging current at the sending end is nothing but IC2. ICT is equal to J omega C by 2 Vs. So omega ante 2 pi FC, 2 cancel, J pi FC Vs. Therefore sending end current IS is equal to IL plus IC2. So this is the nominal pi method. So for medium transmission lines, first method is end condenser method, second method is nominal T method, third method is nominal pi method. So by using these three methods, we have to calculate the voltage regulation, sending end voltage, sending end power factor, receiving end power factor. Next class we discuss about the problems, and also we derive the ABCD parameters of a medium transmission lines. Determination of ABCD parameters for short transmission line and medium transmission line for nominal T, nominal pi. That is the most important one. మా లక్ష్మి రాసి పంపిస్తున్నావు వాళ్ళకి?
పంపిస్తున్నాను సార్.
ఓకే సరే అమ్మ. సరే అమ్మ, ఈ క్లాస్ ఇంతటితో క్లోజ్ చేద్దాం. నెక్స్ట్ క్లాస్ నేను ప్రాబ్లమ్స్ చూస్తాను. ప్రాబ్లమ్స్ లేదనుకుంటే ABCD పారామీటర్స్ ఇన్ ద మీడియం ట్రాన్స్మిషన్.